In this video, we will see how you can automatically fine-tune controller loop gains for your motor control application using the Field Oriented Controller Autotuner block. In the closed loop simulation model here, we have the plant model containing the motor and the inverter model blocks. Then we have the inner DQ axis current PI controller loops and the outer speed PI controller loop. In traditional tuning methods, you would have to tune one loop at a time manually, which tends to be a difficult and time-consuming process. Field Oriented Control Autotuner simplifies and speeds up this process by automatically tuning DQ axis current and speed loops of your application based on the bandwidth and the phase margin you specify for each loop. This block can be used to tune the field oriented controller gains in desktop simulation. Essentially, it runs auto-tuning experiments for each of the loops by injecting perturbations, recording the output, estimating the plant frequency response, and tuning the PI controller parameters. Let's see how this model is set up to automatically fine-tune the gains using the Field Oriented Control Autotuner block. First, we set up the speed reference profile for the motor. We will let the motor ramp up its speed to reach a steady state of around 2500 RPM using initial controller gains. Then, we will raise the speed reference to 4500 RPM, followed by a reverse in the direction of spin to 4000 RPM to see how the controller performs initially. Then, we will bring the motor speed back to steady state at 2500 RPM and use the Field Oriented Control Autotuner block to run those auto-tuning experiments for the inner DQ current loops and then the outer speed loop. After the block has tuned the gains, we will run the same transients in the motor speed reference and check the controller performance with the fine-tuned gains. With the speed reference profile set, we will set up the Field Oriented Control Autotuner block and tailor the auto-tuning experiment settings. The initial PI gains for the control loops have been set up here using data store memory blocks, and the Field Oriented Control Autotuner block is set up in this subsystem named the FOC Autotuner. This block in the subsystem outputs current and speed loop perturbations to the controllers and measures the resulting controller outputs, motor currents, and speed to tune the gains. To tailor the auto-tuning experiment settings, we will look at the block dialog of the Field Oriented Control Autotuner block. Under the parameters, we see the loops that will be tuned. As we do not have a flux loop, we have unchecked this. We have this option checked to use the same settings for the DQ axis current loops. Under the Tuning tab, let's set the controller requirements for the DQ axis current loops. For these loops, we will set a target bandwidth of 3000 radians per second with a phase margin of 80 degrees. The outer speed loop will run at least 10 times slower than the current loops, so we'll put in a bandwidth of 100 radians per second. Let's set a target phase margin of 60 degrees. The Experiment tab lets us choose the amplitude of the perturbations being injected and the duration of the experiments. Based on the speed reference profile we set earlier on, we will set an experiment start time of 6 seconds with a duration of 0.5 seconds for the D-axis current loop. Likewise, let's start the second experiment for the Q-axis at 7 seconds, which allows enough time for the transients from the first experiment to die down. For the duration, again, let's set 0.5 seconds. For the speed loop, let's set the start to 8 seconds and the duration to be 3 seconds. Now, under the loop experiment settings, for the current loops, the plant type is stable with a positive sign. The sinusoidal perturbations here would represent the perturbations of VD and VQ. For this, we will set a normalized value of 0.15. There is no science to choosing this value. It has to be small enough not to change the operating point of the motor and sufficiently large to excite motor dynamics. For the speed loop, again, the plant type and sign are stable and positive respectively. The perturbations for this loop will be the perturbations in the Q-axis reference current, for which we will set a sign amplitude to a normalized value of 0.1. Under the Block tab, we have selected the start-stop of the auto-tuning process to output experiment times that will allow us to update PI gains after each experiment. Finally, the entire control runs in single precision data type, so we'll match that here. Then click OK. Now that everything is set up, we can just run the model. The experiments will run and the Field Oriented Control Autotuner block will update the loop gains for all the 3 loops. Let us now go check how the controller performance has changed. With the initial controller gains, we see the motor response while tracking the speed reference is slow with a significant overshoot and has a large settling time. Then the 3 experiments for the current and speed loops were run between 6 and 11 seconds, fine-tuning the gains. These gains are then automatically updated to the PI blocks. With these tuned gains, we see the controller brings about a better reference tracking performance with better rise and settling time. Note that you can still modify these auto-tuning experiment settings and further fine-tune these gains for your application. So in closing, we saw how to use the Field Oriented Control Autotuner block to tune the gains of a Field Oriented Control algorithm in the desktop simulation model. You can also generate code from this block and deploy it to a speed-goat real-time machine. You can then auto-tune the gains of your field-oriented control algorithms in real time against the motor hardware.